This conference will now be recorded.
Great. Good morning, team. Uh, Good morning, everyone. So let's start off with the point where we left the other day. Good news, things are going as per the plan. So because of the gap that is created with bank holidays and 12 days of my India trip, 12 plus 14, it's total 16. We have running little away from the planned schedule. Nothing to worry. I have went ahead and revisited the whole plan, journey, and everything. So today is May 9th. By June 9th, we'll complete the whole machine learning and data science journey with three solid real-time use cases. I would like to recall, please pull up your sleeves. It's just one more month left over, and we'll finish off everything. You have done a lot of good work and have put so much of efforts till this point. You were nowhere and tried implementing the two use cases by yourself without even knowing what exactly the model does, how exactly a model works under the hood. So this training model session is all about understanding the uh, broader prospect of each and every model. So as I started earlier, I have already finished two or three slides. This slide's already finished. So now let's complete the rest of the slides. And in this whole module, you'll understand each and every concept I'm talking about. The first use case, we have built a, an end-to-end machine learning project without even knowing anything about each of the model. But here it is not like that. Here you are going to understand every bit of it, so you'll go back and relate the things pretty well. Okay, so let's not waste time and start the work on our plan today. First thing, huh, okay, if you remember last time I have shown you this slide, linear regression formula, and I also explained you what is y, what is n, what is x of I, what is theta of j. This looks quite complex for a layman to start and pick up the stuff and move on comfortably. So I decided to make up a notes on the notations part of it. Notations mean what does each formula parameter exactly mean and how does that work. Okay, so first let's understand the notations. First one, let's understand the notations in this course, in this module. So okay, these notations will help you in understanding the mathematical equations. Perfect. Let's take an example of housing dataset end-to-end project in understand notations. Yes, we did this project successfully, and we all know we also did a revision for this one. So we must be in a fairly good position to understand each and every bit. Now, let's take a number. The letter M is a number of instances in the training dataset. When I say number of instances, you have around 26,000 instances in the training dataset. Okay, now that is M. However, take an example if we have 2000 districts in our dataset. Now, guys, think practically. The total number of the total numbers you have in dataset is different, and the total districts you have in dataset is different. Here, M is the number of instances. When I say number of instances, it's not the total records. It is the total records for one particular field, that is called M. Now, district is one instance, latitude is one instance, longitude is one instance. Like that, if you talk about districts, you have 2000 districts. In that case, M is equal to 2000. Super. Now, x of I is a vector of all the future values. Now what is a vector? Go back to your advanced Python classes where we talked about NumPy, pandas, matrix, transpose of matrix, vectors, and features. Vector is nothing but it is an other form of representing a field in the machine learning formula point of it. Okay. Now, here what I'm saying is x of I is a vector of all future values. When I say all future values, for example, when I'm talking about district data set, or when I'm talking about districts instances of among many other instances, and if I know the expected value, then that is called x. Then x of y is a vector of the future value. Means you may have many other vectors like that. Okay, of the ith instance in the data set. Now, guys, focus. Difference between x of I and y of I is you have 200 instances in your districts, right? For first iteration or the first instance, there is a vector and the vector will have a value. So for the first instance, what is a vector? What is a vector value? For the second instance, what is the vector? What is the vector value? Like that, you will have n number of instances. Okay, till you finish your machine learning formula implementation for all the instances, your vector value keeps changing. Your vector keeps changing. Your vector value keeps changing. This is where your machine learning beauty comes out and it calculates the consolidated output. Now, y of I is its label. Again, you have to go back to our first class. We clearly talked about what is a prediction, what is a label, what is a score, what is an error. Now, label is nothing but that is the desired output value of that instances. Now again, the desired output is not the answer that came out of the solution, yet you have other steps to be worked on it. You need to remember that. Okay. So in this slide, thing is very simple. You need to understand what do you mean by instances. Instances mean in a given data set, you'll have many fields. In that fields, what are the number of records you have for each instance? District can be one instance, ocean proximity can be one instance, like that. Now, for every instance, there's a vector. For every vector, there's a value. Keep in mind that this instance, if you're talking about ith instance iteration will have a vector x, and x of I is the value of that vector. Perfect. Y of I is the label. Label is a desired output. Again, it's a desired output, not a predicted output. You need to be aware of the differences there. Okay, this is the importance of it. Now, let me explain you more practically here. Look at this diagram, guys. This diagram explains you a kind of one second. Let me put this aside. Why is it showing like this? Where is my y of I? I have written y of I also, right? Okay. We have y of I also, but I don't know why it's not showing up. Give me 1 second. What designators are not coming up. Okay, don't worry. I'll make this correction later. Now, guys, this is x of I or x of 1. X of 1 is the first instance run. Now try to understand. Within this x of 1, you have minus 118, you have 33.91, you have 1416, you have 38,372. Now what is this x? This is a matrix. What is it containing? It is containing all future values. Again, don't confuse between labels, futures, predictors. Don't worry about it. It's straightly forward. Labels is nothing but the expected outcome. Okay, future values are the values on which you run some transformations or some formulas implementation so that you'll get a label. Okay, now here this is a matrix. What this matrix is doing is this is containing all future values excluding the labels of all instances in the data set. You'll have one row per instance and ith row is equal to transpose of x of I. Now try to link. Here, what am I talking? I'm talking about a vector. So what is this vector? This vector is, let me take a pen guys. This vector is this bit. Okay. Now, again, what I want you to understand carefully is, let me take a pointer again. Go back here. Now, you understood x of I. Now, let's say we are talking about the first instance. So I put x of 1. Now, this is a vector of all future values. So what are all future values? These are all the future values. Minus 118, 33.91, 1416, and 38,372. Okay, perfect. Now, here there is one row per instance. Now, Amarnath, this is a row. Okay, and this is a column. Now, what am I saying here? I have 4 rows and 1 column, right? There is one row per instance. This is x of 1. If I do x of 1 dot t, that will become a transpose. When I do a transpose, this rows, this 4 rows will change into 1 column, because I have 4 rows and 1 column, that will turn into 1 row and 4 columns. You need to remember about it. Now, the ith row is nothing but, here I'm talking about first iteration x of 1. If you talk about x of I like that, when you are working on the ith instance, that is equal to transpose of x of I. Transpose of x of I is nothing but x of I into t or x of I into dot t. Now, logically, if you are smart enough, just understand what is happening under the hood. Okay, you need to be aware of it, because I have seen the Kaggle competitions. They are trying to push you to a corner where you have to pick one of the element in the label and then start working on that. I'll show you the challenge I have faced later. So let's first finish this one today. Now, hope the slide is clear for everyone. Let me move on to the next one. Erase all the drawings and go back to the pointer. Perfect. Now, look here. This is a continuation of my notations. Earlier, you have x of 1. Now I'm talking about x. Okay. Do you see here? Guys, let me take a pen. Earlier, what happened? I have 4 rows and 1 column, which is nothing but 4 by 1. Now, what happened? I have 1 row and 4 columns. Now, this is nothing but, I have to go back here again and explain you. X is nothing but the transpose of x of I. When I say transpose of x of I, like this, every time you are trying to work on n number of instances, that number of instances is equal to transpose of x of I. That's all you need to understand. Now, so guys, in previous page, I explained you about this one. Like that, this is first instance, second instance, third instance, fourth instance. This one comes here, this one comes here, this one comes here, this one comes here. Like that, you have 2000 instances, and for 2000 instances you will have an output, and in that output that will have a vector, and vector will have a label. Now if you exactly ask me to point out a label and show me, I cannot do that, because the machine learning model or algorithm is defined to do it. Now with continuation to this one, we need to understand one other system which is called H. Now let me show you that. I'm navigating between my pen and pointer, so you need to kindly bear with me. Let me go to the pointer. Now look at this formula here. For example, if a model is predicting that median house price in the first district is $158,400, then this will be the formula of that. Y cap is equal to H of X of 1. So this is first district he is talking about. Now you also need to find the prediction error, and the prediction error is nothing but Y cap of 1 minus Y of 1 equal to 2000. Perfect, that is fine. Now how can you do, or how can you find the errors? You find the errors using root mean square error. We are not jumping into root mean square error yet, but we need to understand the formula of what is X and what is H. X we already discussed. X is equal to the vectors labels, and if you're talking about one particular instance, that particular instance vector labels can be found, and overall X is nothing but a matrix containing the outcome of each of the instances. When you talk about vector labels, just when you're talking about vectors, just remember each of the instance vector label will be initially a row, many rows and one column. But when it comes to X, it will be a combination of all the instances outcome, which is converted into one row and number of columns, because each row will have each instance output. That is what I was trying to explain here. Where, one second, let me erase all the drawings and let me go back to the pointer. Guys, you need to understand this. If you understand this, again I'm saying I'm trying to give you the best fundamental building blocks for your data science journey. This will help you to do better. So please focus and concentrate. If you are stuck, just stop me then and there and tell me, Amar, this is not clear to me. I think I can do this bit. It's already saved. Guys, this slide I need to make some changes because I have to add other diagram which is y of I. I think that is underneath this one. Let me see. Oh, two diagrams came. Huh? Let me remove this one. See, see, see. One second. I know this will happen. This is what the problem is when you do improper formatting. Perfect. That's okay. This is what the correction I wanted to say. File, save. Now, if the district model presentation data science training. Perfect. Now, if, for example, let's spend one more minute on this one. This is longitude. Okay, one of the feature. Latitude, other feature. Inhabitants, other feature. Median income, other features. So here x of I. When I say x of I or x of 1 or x of 2, I'm talking about one particular instance only. When I talk about X as a whole, then I'm talking about all the instances outcome. Please be aware of this difference. When I say X of 1, that is for first instance only. When I'm talking about X, that is the whole outcome of all the instances. Now, X is always a matrix. This matrix will have future values. Future values means this is the future. This is the input you are going to give. Now, there is one row per instance. This is one row. This is one row. This is one row. This is one row. So this is one row per each instance. Okay. Now, the ith row is equal to transpose of x of I of t. This one I explained you just now in the converted format of x of I of t and x of I. Okay. This makes sense to us. Now, you understood this one also. Here we are talking about a new thing which is called y and h. To explain you y and h, I have brought you here in this formula. If you see here, y cap equal to h theta of x into is equal to theta of t dot x. All this while you only know about x. You don't know about y cap, you don't know about h, and you don't know about theta also. Let's not jump into that. Now, h is system's prediction function. So we are talking about linear regression. So linear regression will have an hypothesis function that is called h. So h is the system's prediction function. This is also called as hypothesis. Makes sense. When we train a model using instance future vector using x of I, again, instance future vector x of I. If I'm talking about kth instance future vector, it will be x of k, because x of a will have ath instance future vector, x of b will have b instance future vector. Like that, when I'm going to train a model using my any instance future vector, you will always get a predicted value y cap equal to h of x of I. Perfect. Now, what is the establishment of relationship between y, h, and x? You know x of I pretty well. I'm happy for you. You know you need to find y, what is y and what is h. Perfect. To do that, we are going to navigate a bit more. Now, this is the formula, boss. Okay. If a model is predicting, this is the formula. Now, root mean square error is measured on set of examples using hypothesis h. In your mathematics, when you were in school, hypothesis is an assumption. Hypothesis is if you give this value, you will get this output. Left hand side equal to right hand side. Left hand side, if x of uh, if a equal to b dot c, okay, and if a equal to 45, what is the value of c? Okay, what I would say, 8 5s are 40, 9 5s are 45. So I have to put b equal to 9, c equal to 5, like that. Now, in general, what we'll use is, we'll use the lowercase italic letters for the scalar functions of m or y. Now, you use lowercase bold font for vectors. Lowercase bold font means, again, you need to understand, whenever you look at diagrams, whenever you look at the formulas, you'll see few things bold. That bold with lowercase is for vectors. Always remember, bold font for vectors. Again, uppercase bold for matrices. If you see an uppercase and a bold, that is a matrices. Moving forward, I'm not going to explain you what is x and what is x of I. Always remember, x of I will be in lowercase because you're talking about vectors. The uppercase x with bold is a matrices, means it will have a matrix. When you're talking about matrix, that can transpose. When I'm talking about transpose, that can convert your row per instance ID into columns when the real formula is implemented on top of it. Okay, now this is actual formula. We have already read through this slide, but this slide when I try to understand myself, and when I gave it to one of my friend who is a big data guy, he said, Amarnath, I'm quite not comfortable in understanding this slide because it seems a little complicated for me. That's the reason I went back and prepared some other slides for you. Okay. Now, hope you understood what is X. Hope you understood what is X of Y, and hope you understood what is Y. H and Y, we are going to talk more detail in next few minutes. Okay, so don't worry about it. You need to only understand X and X of Y. X is a matrix. X of I is a label vector. That's it. Now, this also we understood. In general, how we use the notations. If you have a small letter in bold, that is a vector. If you have bold letter for matrices, then that is X. Okay, perfect. Making sense? We are cracking it slowly. Now, I want you to forget the slide for now. Okay, let's move on this one. Here, let's look at a simple linear regression model. If you are aware, I have very nicely explained you the GDP per capita or life satisfaction and how the GDP per capita makes people happy in their life. I told you that. Now, here, let's take that example. If you talk about life satisfaction versus GDP per capita, when a person is earning more, is he happy? Okay. Now, what happens here is we have taken several considerations. The formula is this one. Life satisfaction equal to theta of 0 plus theta of 1 into GDP per capita. Now, theta 0 and theta 1 are model parameters. Now you can ask me what the heck is model parameter. I have very clearly explained you a model parameter is nothing but it is the value that it will consider assuming a value and try to run on the instances label vectors and give you an final matrix. Now, let's say, for example, let's say our model has learned the parameter theta of 0 and theta of 1 as 4.8y in 4.85 and 4.91. Now, don't ask me how did the machine learn the parameters. This learning the parameter is nothing but you're training a model. When you train a model, you need to know what are the features, what are the labels, and what are the coefficients, and what these things will come out when you train a model and you experiment the various attribute combinations. Okay. Now, theta 0 is one parameter which machine is assuming. Theta 0 like theta 0 been assumed, theta 1 is also assumed. Very good. Now the final equation will come like this. Okay, where theta 0 is equal to 4.85 and theta 1 is equal to 4.91 into 10 power minus 5. Now you may ask, what the heck is this guy saying? What is this 4.95 into 10 power 5 and what is this 4.85? Again, as I said earlier, park it for now because we already discussed this, but you just have to go back and relate it to here. Perfect. This is good. Now, if you look at it, the whole formula comes here, and this is the how your linear regression graph looks like. Okay. Now, it's our core responsibility to understand why this line came here, what the hell is happening under the line, and what the hell is happening above the line. How can I tell to business, and how can I make a beautiful storytelling in this graph? That is where we are the mature data scientist and real-time data scientist or machine learning experts, I would say. Okay, this is what it is. Let me erase all the drawings. Let me come back to the pointer. Now, let me go to this slide. Okay. You may ask me, Amarnath, this is going over my head. I don't understand what you're trying to say. What the heck is this formula doing? Okay. Now, I'm going to explain you that in more easier way. This equation is nothing but we can find the life satisfaction value from an unknown GDP per capita. That's all it is. Now, but finding the life satisfaction value for GDP per capita of 33,000, if we take an example, again, guys, you are finding a life satisfaction value for an unknown GDP per capita. Okay. So for example, let's take the GDP per capita equal to 33,000. So what happens here? I have given the 33,000 here. Okay. Now, by plugging in the value of equation, which is equal to theta of 0 plus theta of 1. So my theta of 0 is 4.85. I have been telling you. My theta of 1 is 4.91 in 10 power minus 5. And it is 33,000 is the GDP per capita. Now, the line of equation is called y equal to mx plus c. Again, we need to understand about this one. Here, you are getting y. And did you notice that previous equation is an equation of a line? Now, what I mean to tell you here is, do you understand that h equal to y cap blah blah something we did, right? Okay, erase all the drawings, go back to the pointer. See here, if you understand or if you read this carefully, y is equal to h theta of x, h theta of x, which is equal to transpose of t dot x. Perfect. Okay. Now, here, what is y? Again, come back and relate your y concept over here. How can I do that? Erase all the drawings, go back to the pointer. Now, here, you understand that here, you understand that the previous equation is an equation of a line. Perfect. Now, let's understand each and everything carefully. So start questioning, what the heck is y-intercept now? What is this slope of theta 1? What is this c? What is this m? Now, this line is nothing but the line I have shown you earlier in the graph. How did this line come? Now, this is x-axis, I know. This is y-axis, I know. When I say y equal to mx plus c, this m is nothing but a slope. But I also need to know how this slope came. Y slope is theta 1. Then what is my theta 0? Yeah, I'm coming there. Okay, let me erase all the drawings again. Now, my pen is here. This is my theta 0 slope. This is my theta 1. Sorry, this is my theta 0, that is theta 1. Now, whenever you're talking about linear regression, always remember the final output you are seeing on your in your graph using matplotlib is implemented on this formula in the background, where you have a prediction and that prediction will use a formula of theta 0 plus theta 1, and for the first theta 1 is the slope. The first theta 0 is y-intercept, and second theta 1 is a slope. Now you need to understand what is slope and what is y-intercept. Okay. When you talk about slope and intercept, it is again taking you to this formula, which is, 1 minute guys, pointer, this formula. Okay, now a linear model makes a predictions by simply computing a weighted sum of input features. Input features is nothing but each instance feature label or each instance feature vector plus a constants bias term. That constants bias term is nothing but just an example I have shown you just now. Okay. The constant bias term is nothing but it can be your y-intercept, it can be slope. Okay, let's recap now. A linear regression is nothing but, or a linear model nothing but a prediction by simply computing the weights of some input features. So your input features, you have, for example, I said I have 200 features of my district data set. So the weighted sum, what is the weighted sum of first one, second one, third one, fourth one? First, it will sum up everything. And then it will work with the constant term called bias term. In this bias term, you have a slope value and an intercept value. Okay, this one is slope and intercept. One more thing I want to highlight here is notations. So y is your predicted value, n is number of features. There I said m, here I'm saying n. So m or n doesn't matter. It is the number of instances. X of I is ith feature value. Theta of j is the jth modal parameter. Now again, modal parameter means theta of 0 and theta of 1. Theta of 0 can be your intercept value, and your theta of 1 can be a bias term, because the reason why they're important is, look at this graph. Look at this graph. Okay, this graph here is showing it like this based on these values. If these values are changed, instead of going here, it might have gone like this, like this, like this, or like this, or it might have gone like this, or it might have fallen like this. So you need to understand carefully what is this intercept values are and how does they really work. Okay, let's jump into that right now. I'm really having a tough time navigating between point and pen. I need to find out a better way for that. Perfect. So now we understood this. Let me take a last one. Now, okay, forget about the formula now. You are a layman and you need to question what the hell is the y-intercept theta of 0 and why is it 0? Okay. The reason why it is 0 is, you have seen a linear regression graph, line of graph showing from going top from bottom left, it's going to top right. That's after implemented the formula. Now don't worry, you have not implemented any formula. Let's start from basic. This is your x-axis. This is your y-axis. And you know origin OO. Perfect. I appreciate that. Super. Now this is your y equal to mx. What is the formula? Y equal to mx plus c. Now c you can consider as the slope or intercept. Now you know what is x. Again, this is small x, not big X. When I say small x, that is your instance vector. Now what is m? M is number of instances. Perfect. Now, if y-intercept is 0, then the line will pass through the origin. So the first assumption is the y-intercept will always start from 0, so that it starts from the standard origin and then start building up, so the graph can go from the base root to the expected outcome. One more thing I want to highlight here is, if it is not 0 for any reason, if your y-intercept theta of 0 is not 0, then you're starting from the wrong point. It is like you have your roadmap ready and you know where you are starting from and where you're heading to, but unfortunately you were drunk, you went to some other place and starting your journey from there. That is the importance of y-intercept theta of 0. Okay, if y-intercept is 0, then the line will pass through the origin 0, 0. Initially, any formula, any instance you take in linear regression, that will have y equal to mx plus c, and it starts from the line of graph for the slope value or intercept value. Intercept value theta of 0 will always be starting from 0, which is a base point. Okay, this is the important thing you need to understand. Okay, theta of 0 y-intercept. Now the reason why we need to be aware of this one is, you will see a lot of dots falling up the line and few falling down the line. Okay, any way it works, it has to have a defined implementation strategy, which is nothing but from scratch, theta of 0 will be 0. That is what it is. So with this one, we understood the linear regression formula 25%, and we will resume it again tomorrow. As I'm traveling to work and it is taking quite long time to drive, I'm having the sessions very short. We started at 5 and we finish at 5:45. Tomorrow also I'll have a short session every day morning, 1 hour. Today it's only 45 minutes, which I'm aware of. So we'll have 1 hour sessions every morning, and weekends we'll have long sessions. I'm here to help you. So the face recognition worked pretty well on Windows. I have spent a lot of time over the weekend, and this Saturday morning, sharp 9, let's catch up. Let's start doing it, and then we'll continue the rest of the things. Okay. Thank you guys. Have a great day and enjoy your work. See you all in tomorrow's session. Tomorrow we'll continue on this one. Thanks a lot.